Periodicity 3. Trends in chemical properties. The essential idea: elements show trends in their physical and chemical properties across periods and down groups. Nature of science. Looking for patterns. The position of an element in the periodic table allows scientists to make accurate predictions of its physical and chemical properties. This gives scientists the ability to synthesize new substances based on the expected reactivity of elements. Understandings. Oxides change from basic through amphoteric to acidic across a period. Applications and skills. Prediction and explanation of the metallic and non-metallic behavior of an element based on its position in the periodic table. Discussion of the similarities and differences in the properties of elements in the same group, with reference to alkali metals in group 1 and the halogens in group 17. Construction of equations to explain the pH changes for reactions of sodium oxide, magnesium oxide and phosphorus oxide, and the oxides of nitrogen and sulfur with water. Group trends should include the treatment of the reactions of alkali metals with water, alkali metals with halogens, and halogens with halide ions. So, chemical properties. Chemical properties refer to the changes that may occur when one substance reacts with another to make a new substance. For example, the ability to react with a given element family or compound. Combustibility or oxidation reactions, or pH or acid-base behavior. Chemical properties depend on the number of valence electrons in the outer energy level and are related to atomic properties like ionization energy and electronegativity. We've got lithium, carbon and fluorine here. Lithium is a very reactive metal, fluorine, very reactive non-metal, and carbon somewhere in the middle. It's a less reactive non-metal. Lithium can lose electrons easily. This is because it's got a low ionization energy. Fluorine gains electrons easily because it's got high electronegativity. And again, carbon is intermediate. It has intermediate ionization energy and electronegativity. The chemical properties of group 1 metals. The trends in reactivity of group 1 metals are determined by the ionization energy. We've got lithium, sodium and potassium there. Lithium has the highest ionization energy, and as you head down the group you get a lower ionization energy. Like potassium's got the lowest of those three. So it's more difficult to remove electrons from lithium than it is from potassium. And so lithium is less reactive than the more reactive potassium. Reactions of group 1 metals with halogens are synthesis reactions. The general equation for the reactions are the metal reacting with the non-metal diatomic halogen, which gives us the metal halide, which is a salt. And so a metal and the halogen give us a salt. For example, reaction with sodium and chlorine. Sodium metal reacts with chlorine gas to give us solid sodium chloride, which is table salt. The reaction of sodium with chlorine is a vigorous exothermic reaction. You can see the image there. It gives off a lot of heat and light. When different alkali metals react with the same halogen, the reaction strength or rate or vigor increases down the group. So metal reactivity increases as you go down the group. The chemical properties of group 1 metals with water. It's a type of single displacement reaction. Group 1 metals react with water to produce hydrogen gas and a metal hydroxide solution. The general chemical equation is here. You get metal reacting with water to give the metal hydroxide and hydrogen gas. You can see that the hydroxide is obviously a base, and it can be detected using an acid-base indicator. For example, you could use phenolphthalein, which turns pink in a base. Let's have a look at the properties of group 17 halogens. You've got to be familiar with the colours and states of the halogens at 25 degrees. Fluorine is a very pale yellow gas. Chlorine is a yellow-green gas. Iodine is a dark purple grey solid. And bromine is a reddish-brown liquid. The trends in reactivity of group 17 halogens are determined by the electronegativity of the atoms. Fluorine has the highest electronegativity. Of these three, bromine has the lowest electronegativity. So fluorine has a great ability to gain electrons, and bromine has a lower ability to gain electrons, and therefore the fluorine is more reactive and bromine is less reactive. Single displacement reactions of the halogens. The more reactive halogens can displace less reactive halogens from salts. So more reactive halogens move in and kick out the less reactive halogens from salts. And so here we'd have the X2 is more reactive than Y. And so it can move in and it replaces the Y and forms this new salt. The halogen activity series is the order they appear in group 17. So fluorine is more reactive than chlorine, then bromine, then iodine. So which of these will occur? Let's have a look. Well, chlorine is more reactive than bromine. So the chlorine is going to move in and kick out this bromine or replace it. Yes. Next, will chlorine move in and replace the fluorine? It won't, will it? Because the fluorine is more reactive. And finally, will bromine react with sodium iodide? Well, the bromine is more reactive than iodine, and so it's going to move in and it will replace it. The single displacement reactions of the halogens continued. Equations can be written as ionic equations. You can see here the normal equation shows the bromide ion ionically bonded to the potassium here. You can't separate that out though, so the chlorine still looks the same, but you're writing the cation and anion separately. Okay. The potassium does not change or react at all. You can see it's 2K plus here and it's 2K plus here. It's called a spectator ion. Spectator ions can be removed from the equation, giving a net ionic equation. And the net ionic equation would just include the bromine anions. The bromine ion as a reactant and the chlorine anion as the product. Have a look at this table. You can see the acid-base character of oxides. Okay, we've got basic oxides are formed by metals on the left side of the periodic table and are ionically bonded with oxygen. So you've got all of these lilac coloured oxides which are strongly basic. Okay, then you can see we've got the acidic oxides are formed by non-metals on the right side of the periodic table and are covalently bonded with oxygen. So these here, the darker reds, the strongly acidic oxides are covalently bonded to non-metals. The amphoteric oxides are formed from elements with an intermediate electronegativity, and that would be the I guess lighter lilac colour here and the salmon pink coloured here of the germanium oxides, silicon oxides, etc. This is another table. You can see we've got the we're going across the period from sodium all the way along to chlorine oxides here. You start off with the basic oxides, amphoteric in the middle and acidic, similar to the last table we showed you. The basic oxides, sodium oxide and magnesium oxide, they both react with water to give hydroxides, okay, and so they are basic. The silicon oxide and the aluminium oxides don't react with water, so you're not going to get any pH change. The phosphorus oxide, sulfur and the nitrogen oxides give acidic reactions. So you get the phosphoric acid with when phosphorus oxide reacts with water. We're getting sulfuric acid forming when sulfur trioxide reacts with water. We're getting sulfurous acid when the sulfur dioxide reacts with water. We're getting nitrous acid and nitric acid when nitrogen dioxide reacts with water. But if there's plenty of oxygen about, then the nitric acid will only give, the nitrogen dioxide will react with water to only give nitric acid. And it's these, with the 3 stars, that contribute to the formation of acid rain, and we'll talk about that a bit more in the acid and base unit later on. Splendid. Goodbye.